Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes 3rd edition, and we're doing problem number 7.6. The problem statement says, suppose you pour a gallon of water on a yowling cat 10 feet below your bedroom window. Part A. How much potential energy in feet-pounds force does the water lose? Like the potential energy it loses as it's falling, right? So it's up here, and then it drops down to there, right? So as it's traveling this distance, it has a force over a distance, right? So that's the amount of potential energy that it's losing, right? Okay, so we know that the volume of the water is 1 gallon, so I turn that into meters cubed. The height is 1 foot. No, it's not. It's 10 feet. I wrote 10 feet here, so I'm pretty sure this is correct. Yeah, it's 10 feet. There we go. The mass is the volume times the density. So density of water estimated about there. Okay, we already know what the volume is. They gave that to us. So that's kilograms of water. Okay, part A. We need to calculate the potential energy when it's up, right? Okay, so mass times gravity times the distance. Okay, so we've got mass, gravity, distance. And that's what it is in Newton meters. We can convert the newtons into foot-pounds, or into pounds force, and we can change the meters into feet, so foot-pounds. Yep. Okay, so we do that conversion, right? Okay, so that's how much it loses, because it starts up here, falls all the way down until it hits the bottom, and then that's how much potential energy it loses, is however much potential energy it had, unless you want to factor in like the height of the cat and things like that, but I didn't do that. All right, part B. How fast is the water traveling just before impact? Okay, assume that the water is a block of ice. Okay, because water, if you have a fluid moving through a fluid, that gets really complicated really fast. Okay, so I don't think that since you guys, if you're taking this class for the first time, you probably haven't done any like fluid mechanics or momentum transfer or things like that. Momentum transfer within a fluid. I'm assuming we're not doing that. We could get really complicated with this. So it's like asking like, why are raindrops the shape that they're shaped? I think there's a YouTube video you guys might be interested in. Somebody doing like a what if all of the rain fell in a single drop? What would happen? And then they kind of explain like why that wouldn't happen, because rain drops into little particles, right? But in this case, if we assume that all of the ice, right, stays together and it doesn't break into little particles, and we also assume that the wind or the air resistance is much smaller than the force of gravity for the entire time that it falls, then we can kind of neglect this and say that it equals 0, okay? Then the potential energy, if these things are true, then the potential energy equals the kinetic energy, okay? So when it hits the ground, it's going to be going 7.7 meters per second, which is way overestimating what actually is how fast it's actually going. And that is 25.4 feet per second. Okay, so really fast, but not really. It's not really going to be going that fast, okay? Okay, so part C. True or false? Energy must be conserved. Therefore, the kinetic energy of the water before impact must equal the kinetic energy of the cat after impact. So I think they're joking. I mean, obviously this is kind of a joke question, but like after the cat gets splashed, it's probably gonna like yowl and jump away, right? Like it's gonna be like totally flustered. So kind of funny, kind of like hey, yeah, it was splashed, and the cat's energy is now going to be, whatever you splashed it with, right? Sure, like yeah, kind of a joke answer. Yeah, like, okay, maybe the cat could jump 10 feet after you splash it with water, right? Kind of funny. Anyway, the other answer is that I thought of is like, okay, maybe the cat is like totally flat, right? So all of the, if it really was like a block of ice that you're dropping, right? Then because it all stays together and all of the resistances and everything that I was talking about before, you could totally, all that kinetic energy would go into like crushing bones or flattening the cat, right? Or, and maybe even some of it, hitting the cement, so like going all the way into the cement that it's underneath, right? It could totally flatten the cat. So a lot of that energy is conserved. It would dissipate into heat energy. The ice would break apart. Some of it would go into making a sound when it hit the ground. Yeah, so those kind of things, right? Sorry, this is a little morbid for the cat lovers. I should have like warned you beforehand not to listen to this part. Okay. The other thing is the cat is made of perfect rubber. So what if it's just like a perfectly rubber cat and it's not actually an alive cat? It's just a rubber cat, and he misheard the yowling. Okay. So then when he drops the ice on the cat, the block falls on the cat, and then the cat perfectly reflects the block of ice, and it travels right back up into your hands at the top of the window, right? If you neglect all of, if you assume that it's a block of ice and that there's no air resistance or anything like that, you could drop a block of ice, it would hit the rubber at the bottom, and then it would bounce right back up into your hands with a perfect rubber cat, right? Okay. Anyway, those are a few of the things I thought of. If you guys, yeah, I'm sure I'm talking to the internet. I don't have a big audience, but if you guys have some cool comments on that, that would be interesting to hear your thoughts as to what some other scenarios. I'd like to hear them. So, anyway, hope you guys have a good night. That is 7.6, and hope to see you in the next video. Thanks. Bye.